All right. Good evening, children. So once again, it's great to have all of you on board. So we'll continue with the questions that we have been doing. Okay. So we have been doing different types of questions, for mock and as well as for your upcoming NEET examination. So we are continuing with the same genre. So here is our question, theoretical question of a select and then we will slowly look into different numerical aspects also. Okay. Here's the first question. So in alpha, beta, and gamma rays, so all three of them, if they carry the same momentum, the question is which of them have the longest wavelength? Okay, so all these three rays are having the same momentum. So that is something that we have. Okay, that's given in the question. But they're asking us which one of them will have the longest wavelength. So how to approach this question? You know that all these three are the rays, the electromagnetic rays. You can say now they are asking about the wavelength of these three. So how can we approach? What do you think would be the option? Anybody can go for a guess.
One boy have said D.
D. Okay.
D for donkey.
Okay. Yeah, D is right. But how do we really understand that it is D? Okay.
Kankana, you tell me how
Good.
you
That's
done
right.
it. Put it in the chat box.
So
You can't open your mic.
yeah.
So lambda is equal to h by p, sir.
Correct.
P is constant, so lambda is constant, sir.
Very good. Perfect. Okay. According to de Broglie wavelength, we know that lambda is equal to h upon p. H is called Planck's constant, the constant, and then they have told all three of them have same momentum. So that means p is also same. Constant upon a constant is going to be constant anyways. So therefore, wavelength is going to be same irrespective of whether it is going to be alpha, beta, or gamma. And hence the answer is option D. Very good. Good job. So now let's move on to the next question. Here comes the second question. We'll see that. Okay. Yeah. So let me just scroll it down. Okay. A stone of mass. Okay. So as I'm writing the question, so you guys will be, you sit with a notebook, okay, and a pen or a pencil. Please write down what is the given data. Okay. Let's not waste time. So then and there you write what is given data, and then immediately you have to train your brain to think in the direction of what formula would be a perfect fit. Okay, to approach this particular question. So that should be your thought process. So let me just write down the question. A stone of mass 0.3 kilograms attached to a 1.5 meter long. It's attached to 1.5 meter long string. Okay, it is attached to 1.5 meter long string. Is and whirled. Okay, and it is whirled. Whirled means it has been, you whirl it. So there's a circular motion. Okay, so you just basically whirl it around, or in a circular motion. That is what is the meaning of whirling. So whirled around a horizontal circle on a frictionless table. Okay, on a frictionless table at a speed of 6 meters per second. Okay, the tension in the string is I'm giving you the options. Here we go. Option A, 10 newtons. Option B is 20. Option C is 7.2. And option D is none of these. Okay. So as per this question, you understand the mass of the stone is given 0.3 kilogram. And the length of the string to which it is attached is 1.5 meters, and you whirl it around a horizontal circle. Okay, so that has been whirled around So having all this information, they are asking you, and speed is also given. It has been whirled around on a horizontal table with a frictionless table with a speed of 6 meters per second. Then they're asking what is the tension in the string. Okay, so tension in the string is to be found out. So what can we do here? So who can tell me which force comes into picture when you basically spin?
Centripetal force.
Perfect, centripetal force. What's the formula for centripetal force?
mv square by r.
Yes. Okay. So
So
here
option
the
C is 7.2 Newton.
yes, that's correct. So here the tension is given by the centripetal force. Okay. So the tension is backed by the centripetal force of the corresponding object that is in circular motion. So that is what is holding it together. So centripetal force formula is mv squared upon r. Okay. So here r is here basically the length. So m is 0.3 times v squared is 6 squared, which is 36 upon r, which is 1.5. So you simplify this, you would be getting 7.2 newtons, and that's your answer. Okay, so option C is right. Is that clear? So here we understand that centripetal force, is the concept that is to be used, because when an object is in circular motion, and especially when you're tying it to a string and when you're whirling it around, so the centripetal force is a force which is acting towards the center, and that is responsible for the tension of the string. Okay, so that's how we'll solve this. Moving on to the next question. Okay, let's see the next question. Okay, the distance of center of mass, the distance of center of mass of a hemispherical shell of radius r from its center is. From its center is. So here are the options. Option A, r upon 2. Option B is r upon 3. Option C is just r, and option D is 2r by 3.
Sir, r by 2.
Okay, so these are the options. All right. So what's your answer? R upon 2.
R by
First one
2,
is
sir. Option A.
okay. R by 2. Okay. So option A, R by 2. Fine. So here they are talking about a hemispherical shell. That is correct what you said. So when you take a hemispherical shell, what happens? You know that the center of mass of the hemispherical shell, about the radius r, is like a distance. So you take the distance as r by 2. Okay, from its center. So that's the reason it is r by 2 when you consider, because by symmetry. So when you're going to draw it, children, so you understand that you show just you show a hemispherical shell, the hemisphere I'm drawing. Okay, so this is the hemisphere. So this is the center point O for the hemisphere. Okay, now therefore when you talk about the center of mass, r is nothing but the radius. So when I talk about the radius, we all know that the radius is this particular length. So this is your radius, and therefore when you talk about the center of mass in this particular case, so therefore the center of mass would lie. So again I'm drawing here also the radius. I'm using a dotted line convention. This also length would be the radius. So the center of mass is basically going to lie from its center at distance of r by 2, meaning this particular distance is going to be r by 2. So that is where the center of mass is going to lie, from its center. So at a distance of r by 2, it is going to lie. This is the point of the center of mass. Okay, so that's about it, and hence the option is option A. Okay, moving on to the next question. All right, fine. So here we look at the next question. A non-uniform, okay, a non-uniform thin rod of length L a non-uniform thin rod of length L is placed along the x-axis placed along the x-axis such that one of its ends is at the origin. Such that one of its ends is at the origin. Okay. The linear mass density of the rod. The linear mass density of the rod is given by lambda is equal to lambda naught into x. Okay. Find the distance of the center of mass you must find the distance of center of mass of the rod from the origin. Okay, so from the origin you should find the distance of center of mass. So I'm giving you the options now. First option, L by 2. Second option, 12 by 3. Third option, L upon 4. And fourth option is L upon 5. Okay, so these are the options. Now, as per the question, we understand that a uniform thin rod of length L is being involved here. Okay, and it is placed along the x-axis. Okay, so you place it along the x-axis such as its ends is along the origin. So that is important as per the position of the rod is concerned. Okay, and they have given you the linear mass density of the rod. Relation is given. It is given as lambda is equal to lambda naught x. So having this information, they are asking you what is its distance of center of mass of the rod with respect to the origin. That's it. Who remembers the formula for the center of mass of a particular rod having the linear mass density? There is a direct relationship. Okay. Anybody remembers the formula? You can tell me in case you have the idea for it.
So L by 2.
Okay. L by 2. You got L by 2? It's actually not L by 2. That's wrong. Okay. It's not L by 2. But anyways, good try. So here, first what we are doing, it's not the direct formula that you can say. It's not possible. Here, we will have to bring in the relationship. So first, let's try to understand the element. So let's take a rod. So I'm just drawing it. I'm trying to depict it. So we'll take both the axes. So with respect to the x-axis, the rod is being placed. So let's have a rod. Okay, this is a thin rod that is placed. So let me use a different color so that you will understand. So there is a thin rod that is placed. Okay, now what we do, there is a thin rod and we take a small element on the rod. Okay, from the origin, you want to take it. So let me mark it. So from this point, let me take a very small element on the rod. Okay, that small element will have a small mass. Let me call that mass as dm, and the length also will be small corresponding to it. So we will take it as dx. Is it clear? From the origin, the distance is basically we will take it as x units. So x unit is basically the distance. So having this information, therefore, what is a small mass for that element? They have given us that linear mass density lambda is equal to lambda naught into x for the rod. Now, for a small element, yes.
Sir, the dx distance is L minus x, sir.
Okay, dx is that small distance.
Yes, sir, the small distance is equal to L minus x.
L minus x, we will see it. Okay?
Okay.
Yeah, we will see it. So I'm just trying to explain the scenario. Okay, so for small element, if I'm taking that small element will have a small mass, infinitesimally it's having a very small mass. So therefore, dm and that small length associated for that small mass is dx. Okay, the distance of that small element is x from the origin. So this is what we understand as per the question. So linear mass density lambda is equal to lambda naught into x. So therefore, what will be the linear mass density for that small element? I would go for a differential. So I'm going to go for a differential operator. So you try to differentiate it. So in that case, what would happen? So small element dm having a linear mass density as lambda times dx okay, which will ultimately give you lambda naught times x into dx. So we will get a relationship like this for that small element having small mass. So once you get the relationship, now we go ahead and we try to approach by using the relation to find out what is the center of mass. So we can say x center of mass is equal to, so what is the relationship that we have? We know that it is, you try to integrate, children. So you've taken the small end from the origin, you integrate until the complete length of the rod. So it's integration of 0 to L x into dm upon integration of dm, that is total mass. So we make use of this particular relationship and then we proceed. So this is general formula to find out the center of mass, okay, of this particular element. So here substitute the values that you have. So now let me go and let me substitute it. So this can also be written as integration 0 to L. I'm writing the numerator terms. So 0 to L x. So it is x times. So first I'm substituting the value. So just put x times. Now for dm I'm substituting the value which we have already found out as lambda naught x into dx over the whole divided by, again for the entire mass element it's going to be 0 to L. So lambda naught times x into dx. So this is what we have. Now further simplify it. When you simplify it further, what happens? And you integrate it. So I hope you guys know that lambda naught is going to be constant. Constants can be taken out of the integration. So I can take lambda naught outside. Apply your integration, children. Okay. So what happens? X square dx. X square dx is nothing but x cube by 3. So x cube upon 3. Okay. You can substitute for the whole. So you substitute it and then you find out, you are going to apply the limits. So correspondingly the limits. So here, what are the limits we will take appropriately? So you take the limits and you simplify it. So what is the limits here for x cube upon 3?
0 to L.
0?
0 to L.
0 to L. Okay. And here at the bottom, again you have lambda naught times, what would be the term here? Again, it's going to be this time x squared, right? Because you have just one x term. So it's x squared upon 2. So again, limits are from 0 to L. Okay. Simplify this, children, and tell me what happens. Lambda naught is getting cancelled off anyways. You tell me what is,
3, sir.
how much you get?
2L by 3, sir.
2L by 3. Very good. So 2L by 3. So that's the answer. So you get 2L by 3 when you simplify it. So the correct option is option B. Okay, so 2L by 3. So this is the answer. Is that clear? So that's how you approach and solve this question. Fine. So some integration is involved here. That's it. All right. I hope this part is clear to all of you. So this is the approach. Let's go to the next question without any further delay. Question number 5. Okay. Okay. So here's a question. For a cell, the terminal potential difference for a cell, the terminal potential difference okay, the terminal potential difference is 2.2 volts. Okay, that they have given. When the circuit is opened, when the circuit is open and is reduced to 1.8 volts when the cell is connected to a resistance of 5 ohms. Okay, that is R equals to 5 ohms. The internal resistance of the cell is So let's look at the options. Option A is 10 upon 9 ohms. Option B, 9 upon 10 ohms. Option C, 11 upon 9 ohms. And option D, 5 upon 9 ohms. Okay, so these are the options. So here, as per the question, for a cell, they have given you the terminal potential difference. And how much is that? You see that it is 2.2 volts. Okay, this is when the circuit is open. Under open circuit condition, the cell potential difference is 2.2. But when the circuit is being, when it is connected to a resistance of 5 ohms, they see that it is being reduced to 1.8. So that is the observation. Now, under these conditions, they are asking you what is the internal resistance of the cell. Okay, so how can we calculate what is the internal resistance of this corresponding cell? Fine. So let's try to depict this circuit. Let's try to draw it, and let's try to understand. So how do we draw? You know that cell and internal resistance. So let's say this is the cell. I hope you guys know a small resistance to be put next to the cell, which is your internal resistance. This is internal resistance R. Okay, and this is your cell. So cell terminal potential is 2.2. So this is 2.2 volts. Okay. Now this is being connected. How is it connected? It is connected to a resistance. So let us take the resistance. It's connected like this. And what's the value of that resistance? As per the question, they have given you that resistance is 5 ohms, isn't it? So this is 5 ohms. Okay, so this is the circuit. Now, here we have two information. There are two cases. Under open circuit, what they told, when the circuit is open, so for open circuit, they are telling you that the potential or the EMF of the cell, you can say, just I will write EMF, which is 2.2 volts, right? So that is good. So when it is 2.2 volts, then what is going to happen? Then what is the potential difference across the cell? We will see when 5 ohms is connected. So generally your potential EMF of the cell is 2.2. Okay. Now here, when I'm going to apply the concept of Ohm's law, now I'm just applying Ohm's law. You know that current is going to flow in this particular direction. And who knows the relation for current in terms of potential and resistance? General Ohm's law will be I is equal to, I hope you guys know it. What is it?
E
I
by R.
equals, very good, it's E upon R. Okay, here I am taking R as capital R, but you would see that, I'll write it as R total, okay, E upon R total. Now, what is the total resistance in this particular circuit?
5
You can see
plus
that,
R, small r.
yeah, you have internal resistance also. You can see internal resistance and the external resistor 5 ohms, both are in what combination? It is in series combination, right? So you just need to add them. So it's E upon capital R plus small r. Is that clear? So this is what you get. Okay. So now when you substitute the value, you can see that I is equal to E is nothing but 2.2 terminal potential difference upon capital R is 5. So 5 plus small r, which is your internal resistance. Okay. That's it. Now, what is the potential difference across the cell? So applying the potential difference across the cell, so you can apply it and then you can find out when the potential difference is being applied. So how can we approach this question? Can we use KVL, Kirchhoff's voltage law, and we can find out this particular application? Yes, because they are saying that when R is connected, the resistance is reduced, so it becomes 1.8 volts. I mean, the potential becomes 1.8. So therefore, having that information, we can say that 1.8 is equal to 2.2 minus, now this I into R. I into R is nothing but, that's the formula, right? So minus I into R, the internal resistance of your cell. Substitute, children, the values. So when I substitute this corresponding value here, so what do you get? Go for a simplification. So you will get this as,
Option A, 10.9 ohm.
yeah, so you will get 2.2 R divided by R plus 5, okay, is equal to, so when I simplify it, I'll get 0.4. Then go for a rearrangement. So when you rearrange it, you will see that R is equal to 2 upon 1.8. And how much is that? You get that as 10 upon 9. So 10 by 9 ohms. I hope you guys getting 10 upon 9 ohms. So when you simplify this, you will get 10 upon 9, and that's your answer. Okay, so option A, 10 by 9 is the answer for this question. Okay, so 10 by 9 is the answer. Very simple. We drew the circuit, we understood what is the current, and then based on the question, we saw that when it is reduced to 1.8, that value to be written first. So 1.8 is equal to 2.2 minus IR. Simple. So like this, you substitute and then apply the KVL and find out what is the internal resistance of the corresponding cell. That's it. This is how you approach. Okay. So now we'll move on to the next type of question. Moving on to the next question. Question number 6. Okay. Let me just put it here. Okay. Charges are placed at the corners of a square of side A, small a, as shown. The charged particle placed at A, is in equilibrium. Placed at A is in equilibrium. The ratio Q1 upon Q2 is, okay, first I'll draw the figure and then I'll give you the options. This is the figure. So you have a square like this. So this is A, this end is B, C, and this is D. Okay. Now there are charges, children, here. At A you have plus Q1, at B minus Q2, at C is plus Q1, and at point D you have minus Q2. Okay, and the length of the square is A. Okay, so this is what is given in the question. So having this, the options are, I'll give you the options. So first option, that is option A. So option A is 1. Option B, 2 root 2. Option C, 1 upon root 2. And option D is 3 by root 2. So these are your options. Okay. Option A is 1, 2 root 2, 1 upon root 2, and 3 upon root 2. So you have a square and charges are being placed as shown here in this figure. Okay, so having this information, you will have to solve this question. What can we do here to solve this question? Any idea? So which particular law can be used? So charge Q1 by Q2 is what they are asking. So what can we do here? Apply the Coulomb's force, right? Coulomb's law application. To apply the Coulomb's law, so what happens at point A? You're going to apply it.
1 by root 2.
So what is the nature of the force? Say, now at this point A, now you show what and all are, yeah, what and all are the type of forces that can act. At point A, already there is a charge Q1 placed. So positive charge is there anyways. This positive charge, what are the forces experienced by this charge Q1 due to the system of other charges placed at B, C, and D? That is what we try to understand. So there is going to be a Coulomb's repulsive force due to charge Q1, right, at C. So along the diagonal opposite direction. So if this is your diagonal of the square, so that force is going to be experienced in this direction. So there is one force acting in this direction. Okay, so it is going to be a repulsive force. Then due to minus q charge, you know that there is going to be an attractive force here in this direction. Okay, so we will call this as F1. And here again, due to minus q charge, minus q2 charge at D, again there is going to be a attractive force, so we will call this as say F2. Okay, and same way F3 also there is going to be a force that is going to be experienced, so this is F3. Now because this charge at point A is going to be in equilibrium, so you can say F3 is going to act like this. Okay, so I have shown all the three forces, the orientation of the three forces. Having this information, so we are going to write down the values of F1, F2 and F3. So I want one of you to tell me what are the values. F1 you can tell. So what is the value? What is the answer? In terms of K itself you can keep. Instead of 1 by 4 by epsilon naught, we can keep it in terms of K. So you will get K, yes. And then what you will write?
K Q1 Q2 by
Yeah. So K, Q1, Q2, what? The distance. Because it is A squared, you know that it is the same. The distance is same because it's in the square. Right. Similarly, what is F2? F2 is going to be K,
Q1 Q2 by A square.
K, Q1, Q2 upon A square. That's correct. So then what would be F3, children? F3 would be K this time.
Root 2 K Q1 Q2 by A square.
So K, Q1 for F3. It's K, Q1 square, right? Because Q1 into Q1. Isn't it? Square. Is that clear? So you write down each of the forces. Once you've written each of these forces, now you find out what is the resultant of all of them. So what is the resultant of the forces? For F1 and F2, you can find the resultant first. So the resultant of F1 and F2. What is the resultant? The resultant of F1 and F2. So we can find out both the resultant. So imagining them to be the sides of the parallelogram. Now in this case, because it's a square, the angle between them is going to be 90, right? So what happens? Cos 90 term that will go. I hope you guys know the formula for resultant, right? So Fr is equal to under root of F1 squared plus F2 squared plus 2F1 F2 cos theta. Here theta is 90, right? Between F1 and F2. So you would only get F1 squared plus F2 squared. So what's the answer for that? You can see F1 and F2 both are same. So can I write this as under root 2F squared? Because both are same, magnitude is same. So we can write it as under root of 2 times F squared. So the values are, for F square is, you have K squared, Q1, Q2 the whole squared. So which is Q1 squared times Q2 squared upon A to the power 4. This is what you guys get. Okay, simple. So when you get this final expression, so how can we write this? So you can take all the square terms outside.
K Q1 Q2 by A square.
Yeah, see this root 2 under root 2F square, we can directly write it as F root 2, isn't it? So can also be written as K times Q1 Q2 upon A squared into root 2. That's it. So that's the value of the resultant for F1 and F2. So this is the value we get. So once you have the resultant for F1 and F2, now for the equilibrium condition, let us now apply. So for the equilibrium condition, what happens? Here at equilibrium, we can say that this has to be equal. So this resultant should be equal to the other force which is going to act. There is to be found out these two resultant. That is here. So this and this both have to be.
So Fr is equal to F3 sir.
Exactly. So for equilibrium condition, your resultant Fr should be equal to F3. As simple as that. So Fr found out as K Q1 Q2 upon A squared into root 2 should be equal to F3. Who can tell me the value of F3?
Sir,
K Q1 squared
by root over root 2.
Yeah, that root 2A the whole square can be written as A squared, right? So we'll get it as 2a squared. Then what gets cancelled here?
A square will cancel, sir.
A square gets cancelled, okay. And
Q1 and Q1 square will gets cancelled. K will cancel, sir.
yes, yes, correct.
Uh,
So what are you left with? One Q1 also will get cancelled off. So
yes, sir.
we wanted the ratio of Q1 by Q2. So what is Q1 by Q2? Now Q1 by Q2 is equal to,
2 root 2.
are you getting 2 root 2?
2 root 2, sir.
Yes, that's your answer. Okay. So the answer is 2 root 2.
Okay.
So the option here is option D. So option B is correct, which is 2 root 2. I hope this is clear, children. So this is how you approach and you simplify and then solve it to find out the ratio, okay, of both the charges. So let's now move on to the next question, question number 7. Okay, moving on. Okay, acceleration due to gravity is G on the surface of the earth. Okay, then the value of acceleration due to gravity then the value of the acceleration due to gravity at a height of 32 kilometers at a height of 32 kilometers above the earth's surface above the earth's surface is, so here you will have to take the radius of the earth is given RE, which is 6,400 kilometers. Okay, that's the given data here. Now based on this, options are option A 0.99 G, option B 0.8 G, option C 1.01 G, and option D is 0.9 G. Okay, these are the options. So they are asking you what's the acceleration due to gravity at a height of 32 kilometers above the surface of the earth, provided the radius of the earth is 6,400 kilometers. Okay, now again, what's the relation? I hope you guys know the acceleration due to gravity at a height h above the surface of the earth. Okay, so we have the direct formula, the acceleration due to gravity at a height h, so we can write g dash is equal to g upon 1 plus h upon re the whole square. This is a simplified version of it. Okay, so here you can substitute in this formula directly. So here when you substitute, we want the answer in terms of g itself, so keep it in terms of g itself. So g upon, what would you get, children, when you go for a simplification? You get 1 plus height is 32 kilometers, so 32, radius of the earth is 6,400. Okay, entire the whole square. So you simplify this, you square it, you take LCM, reciprocate, and then go for a simplification. So what happens in this case? So you'll
So
get the value as
1024 by so 1 second, sir.
yeah, no worries. Okay. So go for a simple fraction, children. Make 32 upon 64 a simple fraction, and then go for an LCM. That's it. Your job is done. That is what you guys will have to do here. Okay. So I hope you guys know how to do that. So
Okay.
yeah. Just try to solve. Give it a shot. I'll wait. think it's getting cancelled now, children. So 32, I think 32 times 200 is 6,400, if I'm not wrong. So you will get G upon 1 plus. Are you guys getting 1 upon 200? The whole square, right? Isn't it? So 1 upon 200 the whole square. And how much is 1 upon 200? 1 upon 200 can further be reduced, and you can write it as 1 plus. Can I write it as 5 into 10 power minus 3? Isn't it? We can write it as 5 into 10 power minus 3. So G upon 1 plus 5 squared is 25 times 10 to the power negative 6. Okay. Now here you can go for an extract common terms. So you try to extract it. So 1 also can be expressed. So how can you express 1? You shift your decimal point in terms of 10 power minus 6. You express, then you add it with 25. Then go for a reciprocal. Then you go for reciprocal limit. So how much do you get? Yeah, it's an easy task. So G plus, how much is it? 1 plus 25 times 10 power minus 6. Take the common out. So that 6 place values you will shift the decimal place, isn't it? I hope you guys know how many significant figures will be there. So 1.000, one more 0, 25 will come. Okay. So how much is this? So approximately, now you see, when you see this value itself, you can easily judge which would be the option. So it is going to be 0.99, isn't it? So yeah, so it is going to be 0.99 only. The way this solution is going on, so this value is going to be 0.99. So the answer is option A. Okay. So based on how you calculate it, you can go for a guessing. Here we can guess easily that the option is A, just by looking at it. Okay. So simplify it, and then you can bring in this particular relationship. So 1 by 1 upon 1.0025 is obviously going to be 0.9. It's very, very nearing. Okay. So therefore 0.99 would make more sense than any answer here. So that's how you do this. Moving on, next, let's go to the next question. This is 0.99. So next question number 8. So let's move on to the next question. Question number 8. Okay. Right. The ratio of radii is basically the plural form of radius. Okay. The ratio of radii of the planets P1 and P2. Okay, P1 and P2 is A. Okay. The ratio of their accelerations due to gravity due to gravity is B. Then the ratio of their escape velocities will be, so options, here are the options. Option A, AB. Option B, under root AB. Option C, AB squared. Option D, A squared B. Okay, so these are the options. So here they have given you the ratio of radii of the planets P1 and P2, which is A, wherein the ratio of their acceleration due to gravity is B, small b. Then they are asking what would be the ratio of the escape velocities of these planets P1 and P2. In terms of A and B, you will have to find out the answer. Okay. Now, what is a formula for escape velocity? One of the easiest formulas in the gravitation chapter. So, who can tell me the formula for escape velocity? Anybody?
Root 2 GR, sir.
Yes, under root 2 gr. So, let's try. Let's find out. So, V escape velocity of planet 1 with respect to the escape velocity of planet 2. That's what we want to find out. So, as you rightly said, the formula for escape velocity is given by root 2 gr. So, very important here, we need to understand that, you know, the gravity for the planets are not same, and hence we have to write them as under root 2 g1 r1. Let me take g1 as the acceleration due to gravity of the first planet, and r1 is the radius of the corresponding first planet. So under root g1 r1 upon under root 2 g2 r2. Further, you can see that this can be simplified, and we can write it as the whole under root g1 times r1 upon g2 times r2, isn't it? So we can keep it like this. Now, how can we express it further? Accelerations due to gravity, already they have given us, right? What is it? Accelerations due to gravity, g1 is to g2, they have already given in the question. How much is that? It is b, right? So this is b times the ratio. The radii ratios are also being given, which is a, b times a. So what's your answer? It is under root ab. Okay, so the answer is under root ab. So option B is right. Is that clear? This was an easy one. Okay, so based on the given data, we have substituted and then we have simplified. Simple. So that's how you do this question. Let's move on to the next one. Question number 9. Let's see it. Okay, here we go. 1 mole of monoatomic gas monoatomic gas behaves ideally at 27 degrees Celsius. It is subjected to a reversible adiabatic compression until final temperature, okay, until the final temperature reaches 327 degrees Celsius. If the initial pressure was 1 atmosphere, then the final pressure is final pressure is. I'm giving you the options. Option A, 1.75. Option B, 0.176. Option C, 1.0395. And option D is 2. So in this question, there is a data that is given. So they've given you that ln 2 equals 0.7. This is the data that is given in the question. Yes. Now what do you understand from this question? They have told that 1 mole of monoatomic gas. I hope you guys know what is monoatomic. Atomicity is 1. Okay. So it behaves ideally. What do you mean by it behaves ideally? Means that it satisfies the ideal gas equation, right? So I hope you guys know what's ideal gas equation. Okay. So that is what it means by behaves ideally at 27 degrees Celsius. And it is subjected to a reversible adiabatic compression until the final temperature is reaching 327 degrees Celsius. So under these circumstances, if initial pressure was 1 atmosphere, then they're asking you to predict what's the final pressure. Okay. So that's the question. So what do you do to your children? So again, make use of it. So under reversible adiabatic compression. So at adiabatic conditions, what is going to be the relation for temperature and pressure, right? So how can we write down the relationships for temperature and pressure? So you can say initial is to final pressure. So T1 by T2 whole to the power gamma is going to be equal to P1 upon P2 whole to the power gamma minus 1. So this is the relation that we need to use here because you have temperatures and pressure relationships coming in. So make use of this particular relationship. Go ahead and substitute. So we had initial temperature, everything in terms of Kelvin to be substituted. So you write this as 300 upon T2 is basically 600. 300 upon 600 whole to the power of gamma. So what is the value of gamma here? So when you go for substituting it, what do you put it there? So it is 5 by 3 equals, similarly here initial pressure, let me take it as Pi, and final pressure you can also write as Pf. Okay, anyways, so we know that 1 and 2, if 1 is initial and 2 is final, so you can keep it anyways. So here it is 2 by 3. Then once you go and then simplify this, so further when you simplify it, zeros you can cancel out, 3 ones are 3 twos are, all that you do, and then you will get 1 upon 2 whole to the power 5 by 3 equals 1 upon Pf, because the initial was 1 atmosphere, so 1 upon Pf whole to the power 2 by 3. Okay, so you can take logarithm here because exponential form, so I use the natural logarithm. So here can be written as 5 by 3 ln, here base value, so ln 2 equals 2 by 3 ln Pf. Okay, so this is the base value. What I've written here is the base value. So then substitute it. So you know that ln Pf equals 5 by 2 ln 2. Okay, simplifying it. So which is 5 by 2 times ln 2 is given in the question as, I suppose it was 0.7 to 0.7. Okay, simplifying it, you will be getting 1.75. Okay, so that's the answer. The answer is 1.75. So using this is how you calculate. For that, formulas you have to be clear. So this particular relationship. So based on the given data only, we are choosing the formula. So what's given? Temperatures and pressure. So use temperature and pressure, connecting formula for the reversible adiabatic compression. Okay, so the answer here was option A. Alright, that's how you do this. Okay. Right, so moving on. So we'll see a different aspect now, a different question altogether. Here comes the next question. Okay, moving on. So a mass M, okay, mass capital M, is suspended by a rope from a rigid support at A as shown. Okay. Another rope is tight and pulled with a force F. Another rope is tied and pulled with a force F. Okay. If rope AB makes an angle theta with the vertical, then the tension in the string AB is. Then what's the tension in the string? So I'm giving you the figure, children, for this. So this is the figure. So we have a rigid support here. There's a rigid support. So from there, okay. So from there is already a rope. A mass M is being suspended. Okay, and then it is tied from the rope. So initially that mass M is suspended like this. This is the initial condition. Okay, this is at equilibrium. This is how it looks. But what they are telling, this mass M is now pulled because there is another rope that is involved. So they are pulling this using another rope. So that rope is being tied at a point and that is being pulled with a force F as shown. This is this another rope. This is rope B. Say this initial rope is A only. Okay. So then the mass is there present like this. Both the masses are same. It might look different here, but it is the same mass. Okay. This is mass M. This is the question. So there is another rope B that is tied at rope A at a point and it is being pulled. Okay. Now this angle that it makes, this angle is theta. That also they are given. So this angle is theta. Having this information, they are asking us what is the tension experienced by the string AB. So AB string, what tension it is going to experience is the question. Okay. So based on this particular question, so we have to apply. So what can we do here, children? This question has so many ways to approach. One of the best ways are there. So you can tell me, generally if we are approaching, we have a free body diagram, we draw it and we show the forces and we solve. Okay, that's the conventional method of solving. Because you have a competitive, this is a competitive question, it requires a competitive approach. Conventional method, you will take more time to solve. Okay, so because you have a competitive question, so you have to solve it in a less time. So for that, there is a separate theorem. I hope you guys might be knowing it. Okay, you can directly use Lami's theorem. I hope you guys are aware about it. The Lami's theorem, right? So tension T is acting here, and here you have force. And due to the block, what is the force children that will act vertically downwards? Weight component will act. So mg will act here, right? So therefore, according to the Lami's theorem, you can simply say T upon the angle that is there. So you have to show all the angles. Okay. So you know that this angle is going to be 90 as per the question. So let me show the angles there. So that is 90. And what about this angle and what about this angle? Okay, sum of all the angles are going to be 360s anyways. Okay, so this particular angle and this particular angle. So how do we write? So if this is theta, don't you think, children, this angle also will be theta, right? If I'm going to draw perpendicular here, you know that alternate interior angles are equal, right? So this is also going to be theta. And don't you think if that is theta, this angle will be 90? So what is this entire angle? Anybody? The entire angle will be, can I write 90 plus theta? Right? So the angle between F and the rope at point A is 90 plus theta. So what is the remaining angle? So this can be written as 180 minus theta, right?
180 minus theta.
Exactly. So we can write it as pi minus theta. Okay, simple. This you can write as pi by 2 plus theta. Anyways, you can use degrees or you can use radians. So that is left to you. Anyways, you can use and express. Now from Lami's theorem, so I will write here. So from Lami's theorem, you can say upon t upon sine 90 degrees equals to force F upon sine of pi minus theta equals to mg upon sine of pi by 2 plus theta. Simple. Okay. So here we want to find out the tension. So keep tension on one side, shift all other terms to the other side. Okay. So keep tension. So how can we express, children? Go for a rearrangement. You can say tension T is equal to, how much is F upon sine of pi minus theta? Sine of 180 minus theta? Yes, I hope you guys know. So T is equal to F upon, so you can say sine theta. That is also equal to mg upon sine 90 is anyways 1. So mg upon sine of pi by 2 plus theta. So sine of 90 plus theta is cos theta. Simple. Okay. So this is a particular relation that we get. So therefore, T is equal to F upon sine theta or mg upon cos theta. So I'll give you the options. I directly solved it. I didn't give you. So I'm giving you the options now. Option A, B, C, and D. Okay. So here are the options. It is F sine theta, first option. Second option is F upon sine theta. Third option, F cos theta. Fourth option, F upon cos theta.
Option B, sir.
Yeah, which one? This option?
2, sir.
Yes. So F upon sine theta, right? So that makes more sense for the tension. So that's right. So it's option B. Second option is right. Okay. Yeah, because this relation is true. In terms of force, they have given us the options. Simple. Is that clear? So this is how you approach this particular question. Draw the diagram, get the relationships, from the diagram itself, and then you simplify. So here we use Lami's rule. We got the answer very fast. So moving on. Next question number 11. Okay. Okay. Two bodies, A and B. Two bodies, A and B, of equal masses are suspended, from two separate massless springs of constant K1 and K2. If the bodies oscillate vertically such that their maximum velocities are equal, the ratio of amplitude of A to that of B is. I'll give you the options. Option A, first option, under root K1 upon K2. Option B, under root K2 upon K1. Option C, just K1 upon K2. And option D, K2 upon K1. Okay, so these are the options. So they have given you here two bodies. They are given, and they are suspended from two separate massless springs having constants K1 and K2. If they're going to oscillate vertically, then what's the maximum velocities? Then, I mean, if they're going to oscillate with maximum velocity, they're asking you what is the ratio of the amplitudes of both A, that of B. Okay, that's what they're asking. Yeah. So in this case, what can we do with respect to it? So I hope you guys know the relationships. So under maximum velocities, so how do you write down the particular relationships? So whenever they are going to oscillate, there is going to be a angular velocity, right? With an angular velocity, they are going to oscillate, isn't it? So what is the relationship with respect to angular velocities? So we can write down when the bodies are going to oscillate with maximum velocities. So angular velocity comes into picture. So you can write down that ratio of their angular velocity. So both of them, the angular velocities we can express. So angular velocity of A times the amplitude of the first body, so amplitude of A, object A, should be equal to the angular velocity of the second object, spring B, so times the amplitude of the second object. You can express it like this. So because you want the ratios, here we are asking the ratio of the amplitude, keep the ratio of the amplitude on one side, A is to B, so the ratio of amplitude A and ratio of amplitude of the object B. So we can write this as, so we go for a rearrangement, children, you will get angular velocity of B upon the angular velocity of A. That's it. Now substitute the values. So I hope you guys know the relationship. Omega can be written as under root of K by M, right? I hope you guys know in SHM it comes simple harmonic motion. So omega is equal to under root K. For B, B is basically the second one, so K2 upon M. Okay. Similarly, this is under root of K1 upon M. What happens? MM gets cancelled off. What are you left with? So you can write it as under root K2 upon K1, right? And that's your answer. So root K2 upon K1 is the answer. Here, root K2 upon K1, second option. So option B is right. Is it clear? So you make use of this particular relationship. Simple. Okay. So here the formula for angular velocity, omega is equal to under root K by M. Okay. Simple. Angular velocity or frequency of oscillation also you can call it. Okay, of the corresponding spring. So anyways, depends on how it has been expressed. Fine. So the answer is second option for this question. Alright. So we'll do a few more questions before we wind up. We'll go to the next question. So question number 12. the different aspect altogether. So let's see. When a metallic surface when a metallic surface is illuminated with monochromatic light. What do you mean by monochromatic light? Is illuminated with monochromatic light. Mono means single, right? Chroma means color. Okay, single color. Monochromatic light of wavelength lambda. The stopping potential is the stopping potential is 5 V naught. When the same surface is illuminated with light of wavelength three lambda, the stopping potential is V naught. Okay, it becomes V naught. The work function of the metallic surface is let's look at the options. Here are the options. Option A, Hc upon 6 lambda. Option B, Hc upon 5 lambda. Option C, Hc upon 3 lambda. And option D, Hc upon 2 lambda. Okay, where H is Planck's constant, C is the speed of light, lambda is your wavelength. Okay, yes. So for this, we need the relationship with respect to the stopping potential and all those things. So I hope you guys know. This is based on your Einstein's photoelectric effect. Okay, so I hope you guys know the concept behind it. When light of suitable frequency and wavelength is illuminated on a metallic surface, ejections of electrons would take place on the surface of the metal, photosensitive metal. Okay, so that phenomenon is your photoelectric effect. Here, they're asking you what is the work function of the metallic surface. So what's the formula for work function? I hope you guys might be knowing. So you can write work function as, anybody? Phi, right? You can write as phi. Phi. Phi is the symbol for work function. Okay. So here they're asking us what is the work function. This is question mark. So go ahead and substitute the corresponding formula for work function. So when you go and substitute, what's the formula for work function? Let's write that first. Okay. What about Hc in this case? Hc by lambda. I hope you guys know that also. Okay. When you go for substitution, here
Mu, sir.
for each one of them, yeah, Hc by lambda is nothing but mu, right? H, fine. So H nu basically energy. Okay. So now the general formula I'm giving you. So we can write general formula for work function as phi is equal to H nu. Okay. Minus EV. This is the general formula for work function. Okay. So having this information, for both the cases, we are going to now write down the expressions. For the first case, you guys know that the wavelength was, or whatever, lambda, it was monochromatic light of wavelength lambda, then it was swapping potential was found to be 5 u naught. Okay, so for that particular expression, let us write. So if I am writing for that particular expression, then what is going to be your corresponding work function, the expression? So generally I am writing, I'll rearrange and keep the work function on the right side. So I will write it as E. In the place of V, I will put 5 E naught. Are you understanding? So E times 5 E naught is equal to HC upon lambda minus 5. This is for first case. Second case, what they are telling, but stopping potential is now V naught only. So EV naught is equal to HC upon lambda. Now directly we cannot say lambda because it is 3 lambda. So I'm putting 3 lambda, HC upon 3 lambda minus 5. This is for the second case. So then what would happen to the new work function as per both the cases? If you see, if you're going to go for a comparison and contrasting, so we see that your phi, your work function, is now, go and substitute. So when you substitute and go for a rearrangement, what do you get? In this case, you will get HC upon, what is the value? Then we had EV naught, here we have at the bottom EV naught, there it is 5 E naught. So what happens? Go for a simplification. You get HC upon,
4 EV naught.
no, in terms of lambda, is it HC upon 6 lambda or 5 lambda or 3 lambda or 2 lambda?
The HC upon 2 lambda.
Sure. Both the equations now you can take, no? You can just sum up the equations. So what happens in that case? You will get HC upon 6 lambda, right?
Yes, sir.
Yeah, so you will get HC by 6 lambda. Actually. Both the equations, you just, you don't equate for 5, you wanted 5. Okay, just you need to add the equations. So add the equations and then you will get the answer as HC upon 6 lambda. So that is the work function. Simple. So that's your answer. So the answer is option A in this case. Fine. So moving on. Okay. So the last question for the day and then we'll wind up. So it's a different model altogether. Just put it. Yeah. Terminal speed. Okay. Terminal speed of 2 centimeter. Terminal speed of 2 centimeter radius ball in a viscous liquid is 20 centimeters per second. Okay. Then the speed of 1 centimeter ball then speed of 1 centimeter ball, 1 centimeter ball means 1 centimeter radius ball, that is the meaning. Okay, 1 centimeter ball in the same liquid is, okay, in the same liquid is, I'll give you the options. First option, 5 centimeters per second. Second option, 10 centimeters per second. Third option is 40 centimeters per second. And the last option is 80 centimeters per second. Okay, 80 centimeters per second. So we'll have to find out. So for this terminal velocity formula, what's the formula for terminal velocity? Anybody? So the general formula for terminal velocity, hope you guys might be knowing. So Vt is equal to 2r squared times rho minus rho naught into g upon upon 9 eta. Okay, so this is the formula, children. Now here what do you understand? There is a relation between terminal velocity and the radius. How are they related? Terminal velocity is related to radius directly. So the terminal velocity is directly proportional to the square of the radius, isn't it? That's it. So when you say it's proportional to the square of the radius, of both the cases you go and substitute. Okay. So we can write down the square of the radius of both of them. The first case, the second case. So in that what would happen? So we can write this as V1 upon V2 equals R1 upon R2, okay, the whole square, right? It can be expressed like this. So what is V1 then? It is V2 times R1 upon R2 the whole square. Go for a simplification, which is 20 times, this is 1 and 2 square, so the whole is what? The whole square. What's your answer? 2 square is 4. 4 5s are, right? So it is velocity is 5 centimeters per second. That's your answer. Okay, 5 centimeters per second. So option A is the answer. Alright, that's it. That was a direct relationship. So here terminal velocity formula is important. So you must be knowing it. So based on formula for terminal velocity, we could relate the terminal velocity with the radius of the ball. It's directly proportional to the square of the radius, and then we found out the answer as 5 centimeters per second. That's it. That's how you approach this question. All right. So we have looked at different types of questions today. I hope it was helpful. So any doubts you can definitely ask. Okay, based on what we have learned so far, questions that we have approached. Okay.
Sir,
Yeah.
can you send these questions with in our WhatsApp group so that I can refer it again, sir?
Pardon?
Sir, can you send these files, last class and this class files?
Yeah. I'll send it.
In WhatsApp group, sir.
Sure,
so that we can refer it again.
Yeah. Definitely. We'll do it. Okay.
Okay, sir.
Yeah. I'll share it. Last class I didn't do it. I forgot. So I'll share it.
Yes, sir.
Yes. Thanks for reminding. We'll do that.
Okay, sir. Thank you, sir.
Yeah. Okay. Fine, children.
Thank you, sir.
Yeah. Welcome back. Okay. So
Thank
that's it, children. Yeah. We can wind up then. Okay. I'll post it in the group. Say stay connected. Okay. Keep preparing. Give it your best shot. Any doubts you can definitely ask. Okay. Here also or in the group also. No worries. All right. Until then, take care. Have a good weekend. Bye bye.
Thank you, sir.
Yeah. Welcome.